folks, Mrs. White here. Hope things are going well with you. You are staying safe and staying sane. We are getting right down to it, okay? I want to be really clear with you folks. This is the last new thing we are going to be learning today. Or learning for this unit is what I meant to say. I would encourage you folks, if you haven't already, go to the classwork tab and check out the calendar that I have posted there under remote learning materials. It does kind of outline what we're doing every day for classes, and it should let you know kind of what the rundown is for the next couple classes. The next lesson that we're going to cover is going to be a review and practice of this, a lot of this, and it is going to have a couple graphs as our sit and begin. Then we're going to do an official review for Chapter 5 and have a Chapter 5 review assignment. And then we will have the Chapter 5 test. Okay, so I want to be really, really clear. Chapter 5 test coming up in about a week and a lesson. Okay, so keep that in mind that today is our last day of really official notes, and then we're going to be practicing. So this is a little bit of a review of stuff that we've already covered. So first, find f of g of x. So this is asking us to do a composition and to take our g of x function and plug it into the f function and just simplify. So I'm going to take my g of x, which is this, and I'm going to plug it in, boom, right there. So I end up with 2 times, instead of x squared, I'm going to put 8x squared plus 3x. And then I have to close the parentheses and put that squared. Now you might be like, all right, Mrs. White, let's send this squared here and here and here and here. And you could do that if this was a mono, but it's a binomial. It is 2 pieces, so I cannot do that. So instead, I have to, some of you may call it foiling. I know that's what Mrs. Boyce called it. I call it double distributing. We're doing 8x squared plus 3x times 8x squared plus 3x. Okay, and this is a nice review of multiplying polynomials because honestly that was in section 5.1 anyways. So we're going to take this and multiply it here. 8 times 8 is 64. X squared times x squared, when we multiply bases we add our powers, so 2 plus 2 is 4. Then I'm going to take this and send it down here, so 8 times 3 is a positive 24. X squared times x to the first, again we add those powers, I have x to the third. Now I'm going to go and distribute this 3x here and here, so 3 times 8 again is going to be another positive 24, and then x to the first times x squared is x to the third again. So I'm noticing these are like terms. And then I'll send my positive 3x to positive 3x and have a positive 9, x to the first and x to the first, x squared. Now, when I simplify that, I'm not done. I still have to remember I have this 2 in front. So I should go highest to lowest powers. I'll keep the 2 in front for now. My highest power is 4. That's a 4th degree right now. So I have only one of those, 64x to the 4th. I'm done with that. Next, I have an x to the third and an x to the third. So together I have 24 and 24. I have 48 x to the thirds. And then lastly, I have one lonely x squared. So I'm going to add 9x squared there. My last step is going to be to distribute this 2 across to this piece and to this piece right here. Okay? So 2 times 64 is 128 x to the 4th. 2 times 48 is a positive 96 x to the third. And 2 times 9 is a positive 18 x squared. Now at this point, everything is as simplified as it could possibly get. I am done right there. Okay? So composition of functions, if they have an x here, is just taking that whole function and plugging it into the other and simplifying. Again, if you're multiplying a poly and a poly, and specifically here it was 2 pieces, so it was a binomial times a binomial, you have to make sure to distribute everything accordingly before you simplify. Another thing we covered is finding inverses and graphing them. So I'm going to start by finding this inverse by flipping my y and my x locations. So instead of y equals, I'm going to have x equals, in parentheses, y plus 1 squared plus 3. Now I need to get this y right here alone and positive. So I'm going to go outside the parentheses first and get rid of this plus 3 by subtracting it. Then I'm going to have y plus 1 squared over here. Oops, 1 squared. So I can't get in and move this plus 1 over till I get rid of that squared. So I'm going to root and root at this point. So now I have, if I square rooted both sides, now I have the square root of x minus 3 equals y plus 1. At this point, it's easy to get this y alone and positive. I'm going to minus 1, but it's going to have to stay on the outside of my radical sign. So I'm going to have the square root of x minus 3, and then a minus 1 on the outside equals y. Now this is our inverse function. However, we know that to graph it, it's a little bit more work. Okay, so I'm going to start off by taking my radicand, and this is what we covered last class, right? X minus 3. And I'm going to set it equal to the 3 smallest perfect squares. So equal to 0, equal to 1, and equal to 4. And these are going to give me my x values that I'm going to plug in, and then to get out my y values and have my coordinate pairs. So I'm going to start by adding 3. I end up with 3. I'm going to add 3, I end up with 4. I'm going to add 3, and I end up with 7. So my graph is going to have these 3 x values. Now I'm going to plug each of those into my equation over here. I'm going to have 3 minus 3 if I plug this first one in, which is 0. Square root of 0 is 0. Minus 1, negative 1. So if I'm thinking of my graph, I'm going to go over 1, 2, 3, and down 1. Okay. Now in my next one, I'm going to take this 4, and I'm going to plug it in here. 4 minus 3 is 1. Square root of 1 is 1. And 1 minus 1, well, that's 0. So I'm going to go over to 4 and up 0. My last point I'm going to graph is where the x is 7. So I'd put a 7 right here. 7 minus 3 is 4. Don't forget this. Square root of 4 is 2. 2 minus 1 is 1. So I'm going to go over to 7. So there's 4, 5, 6, 7, and up 1. And here is my graph, remembering to start wherever my inside equals 0. This is going to be my kind of vertex almost of my square root graph. So this actually covers 3 sections. It covers 5-2, which was compositions. It covers 5-3, which was inverses, and it covers graphing square roots, which was section 5-4. Okay, we're skipping 5-6 this year, and we're moving on right into solving radical equations. All right, so our new learning for today is going to have us looking at solving radical equations. Okay, so the term radical is letting us know it's not just going to be square roots. It could also involve cube roots, fifth roots. When it could be any root, we call it an nth root. So we're going to be dealing with radicals that could include any type of root in it at all. So we're going to first outline some general steps that we would take to start solving these regardless of what type of root it is. So you'd see examples somewhat like the ones below, where we have this one is a nice little root sign here. I want to refresh your memory that the number, if there is a number right here, is called your index number. And if there's no number there, we just assume that the index number would be 2 and that it's a square root. So here we're dealing with a square root. Here we're dealing with square roots. Here you're like, Mrs. White, there's no roots. Well, there is, and we'll talk about it shortly, okay? When we have a rational or a fractional exponent, that's where our roots are going to come from. So anyways, thinking about solving with general steps, our first step is going to be get your radical sign alone on one half of your equal sign, okay? So you're going to isolate your radical on one side of the equal sign, okay? So if we look over at this first problem in part A, okay, I have the square root of x plus 2 with a plus 4 on the outside equals 7. I need to get rid of this plus 4 as my first step. Here I have roots on both sides, right? But there's nothing going on the outside, so the fact that this root is alone on the left-hand side of this equal sign means we're good to go, okay? Over here, again, once we figure some stuff out about this, we'll realize that we need to move over both the negative 4 and divide by 2 to get our root alone here. So anyways, first steps first, isolate your radical by adding, subtracting, using inverse operations to get that root alone, okay? Secondly, you're going to do the inverse operation of roots. And the inverse operation of a square root would be squaring. The inverse operation of a cube root would be cubing. So what we're going to do is we're going to raise both sides. Because remember, what we do to one side, we have to do to the other. Raise both sides to an exponent that is equal to our index number. So again, that lets us know if we're dealing with a fifth root, we're going to raise it to a fifth power. If we're dealing with a square root, we'll raise it to a second power, okay? The exponent is going to be the same thing as your index number. And then lastly, once you raise both sides to that, you're going to simplify that down, and then you're just going to get your variable alone and positive, okay? Just solve for your variable. Now, you're going to find out, and we're not going to necessarily see it today in the examples that I have for you, but when we practice this again next class, there's potential to see it. Sometimes when you go to plug your answer in, it's not going to work. So you need to actually, as part of the last step, you actually have to check it. Okay, and I know you've probably been told by math teachers forever that you have to check your work, and I am super guilty of not telling you that because I hate checking my work. A lot of the times you check it, your answer's right, and it was a waste of your time. Well, here, you're not going to know that your answer is correct or not unless you check it, okay? Because sometimes when you plug stuff in and you look at both sides, they are not equivalent. So when you check your answer, if you plug it in and it doesn't work, this means you found an extraneous solution. Okay, that's kind of our vocab word. It's going to be an answer that creates an impossible or an inequivalent situation when you plug it in. So it's an answer that doesn't work. I know that seems like a silly definition, okay, for extraneous, but you'll see. Again, today we won't see it, but next time that we are somewhat together, you will. Okay, I'll make sure that I kind of revisit this. So let's look at our first problem, okay? Hopefully you have a general idea about how we're going to go about this, looking at those 3 steps. So our first things first is to isolate our radical, okay? Isolate our radical. I'm going to come down here. Here's my radical sign. It's a square root. There's a +4 on the outside, so my first step is to -4 from each side. I'm left with the square root of x plus 2 equals 3. Is there anything else with this root on the left-hand side here? No, there's nothing being multiplied or added or subtracted outside of it before we hit that equal sign. So I've isolated my radical. My next step is to look at my index, and I'm going to raise that number as an exponent on each side. So my index number here, even though it's invisible, is technically a 2. So to cancel out a square root, I'm going to square it or raise it to the power of 2. And what I do to one side of an equation, I have to do to the other. What's nice is that this cancels out my entire root. The whole thing that makes this a radical function is now gone, right? So I'm left with x plus 2 equals, and then don't forget, you got to square over here. 3 times 3, 9. Last step, -2, -2. And I get x equals 7. My last step is, and I don't care if you do it with mental math, okay, is to make sure you go back and double check that this answer works. So I'm going to put my 7 in here. 7 plus 2 is 9. The square root of 9 is 3. 3 plus 4 is 7. My check is good. And I usually put a check next to my answer just to remind myself I did check it. Now let's say, for example, this was a 6 over here. When I plug in the 7, I get 7 over on this side. It equals 6. That does not work. I would cross it off, okay? And put no solution. We've seen extraneous solutions in the past, right? Things that maybe you plug into a linear equation and everything cancels out except for a 2. And you end up with 0 equals 2, which clearly is a no solution, okay? Let's take a look at this next one. I know this one's a little funkier at first. I agree with you because it has a root on both sides. But our first step is to isolate a radical on one side of the equal sign. So here's my equal sign. If I look over here, this radical is already alone. If it had a 2 in front, I would have to divide 2, divide 2. I just need to get one side alone, okay? And honestly, straight up, it's already alone, so I can just skip that first step. My next step is to raise both sides to an exponent that's going to be equivalent to the index. Again, there's no index shown, so I can assume it's a 2. So I'm going to square it. What I do to one side, I have to do to the other. Those 2 cancel, which means I'm left with just 7a minus 2 Algebra 1 of you loves that, right? It's nice and easy. I have an equal sign. And what's cool about this problem is, look, this is also a square root. Square root and squared cancels. Boom, I'm left with just my inside, just my radicand. Sorry, I don't know why I spaced out on that. A plus 3. Now, hopefully you're like, oh, I can solve this from here. That's nice and easy and something very familiar feeling. I'm going to minus A minus A. 7 minus 1 is 6, so I'm left with 6A minus 2 equals 3. I'm going to add 2. I get 6A equals 5. Divide by 6, divide by 6. I get that A equals 5/6. Okay? Now the last step that I should take is to plug it in and check. Okay? I'm serious. Actually do it, because we are going to find, and I wouldn't tell you this if it wasn't something you were going to say, that you're going to eventually at some point hit a no solution. So I'm going to put 5/6 here and 5/6 here and see what I get. So I have the square root of 7 times 5/6 minus 2 should equal, if this is a 5/6 and I'm adding 3 to it, I'm going to have 3 and 5/6, right? So I could probably just keep that as 3 and 5/6. Okay. So first things first, I really only need to simplify over here. I'm going to put that over 1. I get 35/6. So inside, I currently have 35/6 minus. Now, in order for us to subtract fractions or a fraction and a whole number, they have to have a like denominator. So this 2 is currently over 1. So I times it by 6 to get to the denominator of 6. So I'm going to times the top by 6. So I end up with 35 minus 12, which is 23/6, still under the square root, equaling the square root of 3 and 5/6. Now I need to see if this improper fraction is equivalent to 3 and 5/6. So I do that by making it a mixed number. 6 goes into 23 3 times, because 6 times 3 is 18. 18 minus 23 is 5. Oh my gosh, it is. They're both equivalent. 3 and 5/6 and 3 and 5/6. So it ends up working out perfecto. Okay? I've checked it. Again, I understand you don't love that idea, but it's better than getting the problem wrong when it could end up being an extraneous solution, meaning that it doesn't work. It would create an impossible situation in getting the problem wrong. So like I said, I knew we would get to this problem. We're going to start seeing some problems that have rational exponents. And obviously you must assume that it's related to our radical equations a little bit. So what I have for you folks is a quick little con intro video. We'll just watch a minute or two of, actually a few minutes of, that explains where rational exponents come from.
We already know a good bit about exponents. For example, we know if we took the number 4 and raised it to the third power, this is equivalent to taking 3 4s and multiplying them. Or you could also view it as starting with a 1 and then multiplying the 1 by 4, or multiplying that by 4 3 times. But either way, this is going to result in 4 times 4 is 16, times 4 is 64. We also know a little bit about negative exponents. So for example, if I were to take 4 to the negative 3 power, we know this negative tells us to take the reciprocal 1 over 4 to the third. And we already know 4 to the third is 64, so this is going to be 1/64. Now let's think about fractional exponents. So we're going to think about what is 4 to the 1/2 power. And I encourage you to pause the video and at least take a guess about what you think this is.
So most people think that you would maybe half the 4 is something I've heard a lot. It's not necessarily that you take this and you half it, even though it might at first it might seem that way. So just hang on, he'll continue with the explanation.
The mathematical convention here, the mathematical definition that most people use, or that frankly all people use here, is that 4 to the 1/2 power is the exact same thing as the square root of 4. And we'll talk in the future about why this is, and the reason why this is defined this way is it has all sorts of neat and elegant properties when you start manipulating the actual exponents. But what is the square root of 4, especially the principal root? mean? Well, that means, well, what is a number that if I were to multiply it by itself, or if I were to have two of those numbers and I were to multiply them times each other, that same number, I'm going to get 4. Well, what times itself is equal to 4? Well, that's, of course, equal to 2. And just to get a sense of why this starts to work out, well, remember, we could have also written that 4 is equal to 2 squared. So you're starting to see something interesting. 4 to the 1/2 is equal to 2. 2 squared is equal to 4. So let's get a couple more examples of this, just so you make sure you get what's going on. And I encourage you to pause it as much as necessary and try to figure it out yourself. So based on what I just told you, what do you think 9 to the 1/2 power is going to be? Well, that's just the square root of 9, the principal root of 9. That's just going to be equal to 3. And likewise, we could have also said that 3 squared is, or let me write it this way, that 9 is equal to 3 squared. These are both true statements. Let's do one more like this. What is 25 to the 1/2 going to be? Well, this is just going to be 5. 5 times 5 is 25, or you can say that 25 is equal to 5 squared. Now, let's think about what happens when we take something to the 1/3 power. So let's imagine taking 8 to the 1/3 power. So the definition here is that taking something to the 1/3 power is the same thing as taking the cube root of that number. And the cube root is saying, well, what number, if I had 3 of that number and I multiply them, that I'm going to get 8. So something times something times something is 8. Well, we already know that 8 is equal to 2 to the 3rd power. So the cube root of 8, or 8 to the 1/3, is just going to be equal to 2. This says, hey, give me the number that if I say that number times that number times that number, I'm going to get 8. Well, that number is 2, because 2 to the 3rd power is 8. Do a few more examples of that. What is 64 to the 1/3 power? Well, we already know that 4 times 4 times 4 is 64.
It's okay if you do not remember that 4 times 4 is 64.
So this is going to be 4. And we already wrote over here that 64 is the same thing as 4 to the 3rd. I think you're starting to see a little bit of a pattern here, a little bit of symmetry here. And we can extend this idea to arbitrary rational exponents. So what happens if I were to raise, let's say let me think of a good number here. So let's say I had 32. I have the number 32, and I raise it to the 1/5 power. So this says, hey, give me the number that if I were to multiply that number, or I were to repeatedly multiply that number 5 times, what is that? I would get 32. Well, 32 is the same thing as 2 times 2 times 2 times 2 times 2. So 2 is that number that if I were to multiply it 5 times, then I'm going to get 32. So this right over here is 2. Or another way of saying this kind of same statement about the world is that 32 is equal to 2 to the 5th power.
All right, so let's think about that and apply it to what we're doing right now. Okay, so let's take a look at this example right here. Okay, so we have this intro video that gave us kind of an idea about how the denominator of that fraction is maybe related. But I want to show you what he was trying to get at is that when we take a fractional exponent, its inverse is kind of the reciprocal of that fraction. So like if I were to take 1/2 and do the opposite to it, I would be raising it to the power of 2 over 1. If you remember exponent powers, we would multiply these, so we'd get 2 over 2 or just 1 b to the 1st, okay? So if squaring it, this cancels it out, right? Because we would say, okay, what is this doing? Well, if we square it and it cancels it, that means it has to be the opposite of squaring, which means that it would have to be representing a square root. I know that feels really complicated, okay? So instead, what I would like to do is just give you the shortcut. Okay, so if you're dealing with any number and it's raised to a fractional exponent, so we're going to call this exponent a over b. B becomes your index number, And we know that our index number is our root, right? And then the A, and what happened is in the con video, Saul just showed you principal roots. And what that means is that the A is always 1, okay? We're going to see a lot of ones that have principal roots. That's all we're going to see today, but in the future, you could definitely be seeing stuff that has a different numerator. So this numerator stays as just an exponent on the specific n. So let's say I had n to the 2/5. This 5 becomes my index. So that means I'm going to have a 5th root. And this 2 is an exponent on the n. So it's n squared underneath a 5th root. Now this right here is called radical form. This right here is called, because it has an exponent, exponential form. Okay, so we could do a couple examples like this where we're given something in what we would call exponential form, right? It has an exponent and we're asked to write it in radical form. Or we're given something in radical form and we're asked to write it in exponential form. So if we're given something in radical form, we are going to look at our denominator. That's going to be our index. So we're going to have a 6th root, and then underneath our root sign, we're going to have an x to the 1st power. And we could put the 1, but we don't need to. That's this in radical form. So here we have it in radical form. They want us to make it have an exponent, put it in exponential form. So I'm working backwards. Remember, this came from the denominator, right? So I'm going to have z. That's going to have a fractional exponent. The bottom's 4. What power is technically attached to this z right now? 1. Z to the 1/4. Okay, let's do a couple more. We're not going to do a proof for this. I sometimes have required that in the past. I just want you to understand how we're going to go about them. Okay, so this is radical form. We need to figure out what the exponent's going to be. So we know it's going to be a fraction because we have a root. Our denominator is going to be 3. And our numerator is going to be whatever exponent is attached here, 5. So a is 5/3. Hopefully right now you're already looking ahead to this one and you're saying, oh, I know what this is going to be. My denominator is going to be 5. And my numerator here is going to be 2. So let's work backwards again. Okay, so now we have something in exponential. We're going to put it in radical form. This denominator becomes the index. And this exponent goes attached to that number. And then lastly, one last time, denominator is our index, exponent is our numerator. So 4 to the 1st, we don't have to put the 1 there, okay? But if it makes you feel good, then you can. Just kind of an idea of what those mean, okay? They don't go over that a lot in the book. They just kind of start giving you examples. So now you know what this means, okay? So I might add a new first step on top of this, okay? Is maybe what we do is if it's an exponential, we want to change it to radical form first. Okay, so if you're given something in exponential form with a fractional exponent, your first step should be make it a radical, and then isolate your root sign, and then raise it to a power, and then solve and check. Okay? So with that new learning, I'm going to look, this 1/3 is only attached to this parentheses. So I still have a 2 on the outside. When I see a fractional exponent, I'm going to put it right in radical form. The denominator is 3. The numerator is 1, so that means these stay with the powers they already have. And then I still have a -4, and then I have equals 0. So now this is something we definitely can solve based on what we did here, right? I can add 4. Remember, I need to get rid of both this piece and the 2. I need to do inverse order of operations, right? I'm going to do addition first and then divide by 2. So if I add 4 to each side, I'd +4. Those cancel. I'm left with a 4 right here. Then I would, like I said before, divide by 2, divide by 2. And I'm left with the cube root of 6x minus 3 equals 4 divided by 2, 2. Now we're going to that second step again. Second step is look at your index, raise it to that power. So this is a cube root. I'm going to raise it to the 3rd. What I do to one side, I have to do to the other. Okay? Cancel, cancel. 6x minus 3 equals not 6, it's 2 times 2 times 2. 2 times 2 is 4, times 2 again is 8. Now at this point, it's always like a sigh of relief, right? This is just a normal equation, nothing fancy about it. I'm going to add 3, and get 11. I'm going to divide by 6, and I'm going to get that x equals, another fraction. Fractions happen, 11/6. And I'm going to take a second, I'm going to plug that in and make sure it works, okay? So what I'm hoping is that when I plug in my 11/6 here, it's able to be cube rooted nicely, okay? And then I can double it and minus 4. So I'm probably going to have to do this below. It's going to require a little bit more work. So 2 times, and I'm going to put it right in radical form so I don't have to think about this, the cube root of 6 times 11/6 minus 3 minus 4 on the outside should equal 0. So first things first, I come here. I get 66 over 6, which is the same thing, 66 divided by 6, which is 11. And 11 minus 3 is 8. So I currently have 2 times the cube root of 8 minus 4. And 8 is a perfect cube, okay? You could use a calculator to cube root this, and if it works out nice, great. But the cube root of 8 is actually 2. So I have 2 times 2 minus 4. 2 times 2 is 4. 4 minus 4 is 0. So yes, this does work, okay? So the big takeaway from that Khan Academy video and from what we're doing today is that if you see something that has a fractional exponent, make that denominator your root sign, okay? Then get your root totally alone on one side. To cancel out that root sign once it's totally by itself, raise it to an exponent, and that exponent should be the same thing as the index, raise it on both sides. And then solve it, because your root sign's going to be gone, and check your answer, okay, to make sure that it is not extraneous. I have a couple more practice problems. Let's do 2 more, and then you folks can hop on over to your homework, okay? So let's take a look here. All right, a couple multiple choice ones. Feel free to pause the video. What I'm going to do right now is I'm going to solve this one quietly, and then I'll walk you through my work. Okay, so feel free to pause it. I'm going to solve it. All right, folks, so first things first, I said, all right, I need to get my root sign by itself. I noticed there was subtraction and multiplication to get rid of. So first things first, I'm going to get rid of the subtraction by adding it to both sides. These canceled. Then I divided by the 3, okay, and I got 2 over here. So I had the 4th root of 2n plus 6 equals 2. So to cancel out a 4th root, now that the root was alone on the left-hand side, I raised it to the 4th power on both sides, canceling out my radical sign. And then 2 to the 4th, I had to take a second. It's 2 times 2 times 2 times 2. So I just did some multiplication and figured out it was 16. Subtracted 6, divided by 2, and I got c equals 5. My last step should be plugging that in and making sure it's good. So 2 times 5 is 10. 10 plus 6 is 16. Okay, I just found out 16 is a perfect 4th, I guess. 4 perfect quartic, I guess. Because 2 times itself 4 times is 16. So that means this is going to be 2. 2 times 3 is 6. 6 minus 6 is 0, so it does work. Okay? Let's give a go to our next one. Okay, I notice right now it has a rational exponent. I am not intimidated by a rational exponent. I know my denominator is going to be my root index, and that this one is just going to kind of cancel out. Okay, so if you need to, or I'm encouraging you to, pause the video real quick. I'm going to write out my work, and then we'll get back together. All right, folks, let's come together. So first things first, I said, oh, this fractional exponent, I'm going to rewrite it as a radical. Okay, I'm going to change it from exponential form to radical form. And then I just brought everything else over with it. Then I said I got to add 12, divide by 4, divide by 4. Remember, the order that matters. You have to get rid of your add, subtract first. Now my root sign was isolated, right? It was the only thing on this side, and I knew that I was able then to raise it to the 4th power to cancel out my 4th root. And I raised my 3 to the 4th power. It is not 12. It's 3 times 3 times 3 times 3. It's 81. It's a big number, okay? I minus 6, got 75, divided by 3, and got 25. My last step should be just simplifying and solving here. So 3 times 25 is 75. 75 plus 6 is 81. 81 to the 1/4, or I would look at the 4th root of 81. Well, I know it's 3 because I just found it here, right? 3 times 4 was 81. So this is going to be 3. 3 times 4 is 12. 12 minus 12 is 0. It works, okay? Plus, no solution wasn't an option here, so I was feeling pretty confident about my x equals 25. You have 5 problems attached to the Google Classroom. Each of those are worth 2 points. Okay, so take your time, do your best. If you have questions, feel free to reach out. Feel free to attend office hours tomorrow if you need to. Okay, so it's all going to focus on solving. You're going to have a mixture of ones that have fractional exponents and things that have root signs. Okay, take your time, do your best, show up to office hours if you need to. It's only 5 problems, so give it a go. Thank you, folks. I hope all is well. I will see you later. Bye.